by Nawras and Jinghan. Both of them are PhD students. Nawras' research interest lies in the intersection of deep learning and high computing. He works on advanced translation techniques to accelerate the training of DNNs and exploit underutilized HPC resources, including a lot of supervised learning, semi-supervised learning, and hyperparameter optimization. In addition to this HiDL project, whatever we have, high performance deep learning, we also have a much more bigger project, which is an NSF AI institute called ICYCLE. So Nawras takes an active participation in that project also. And then Jinghan's interest is on the HPC and large scale communication optimizations for AI training and inference. And especially has developed efficient communication runtimes and libraries to accelerate the foundational model workloads. And he has published many conferences, including MLCs, IPDPS, NeurIPS, and I also presented his work at GTC. So both of them together will present this tutorial, which is MPI-driven solutions towards high-performance deep learning training. So what we mean here, what you will see in the presentation, we are taking an approach towards vendor-neutral stack for AI. So broadly, if you talk to any vendor, they say, okay, you are running, let's say, NVIDIA hardware, it has to be nickel has to be used, or AMD nickel has to be used. So we are trying to break from that kind of a silos, and we are trying to see that can MPI runtime itself be used. Like MPI has all these collective supports from many, many years back, all reduce, all to all gather. So the question is, can we get equal or even better performance than nickel or nickel? So that is the focus. So they will go through this tutorial. So what we have actually done, not only the MRP Plus library has been optimized, we have actually modified PyTorch. Okay. So if you are trying to run any training or inference, you remain at the PyTorch without any changes. But the PyTorch middleware layer will be able to link it to our MRP library. Okay. And we have made that GitHub open. Anybody can download, anybody can install. We have made some public builds available, so you don't have to build. So that's what Nawras and Jinghan will be talking about. Okay, you're ready?
We are ready. Okay, can you switch the... Right, perfect. Okay, thank you, Dr. Panda. So yeah, my name is Nawras Alnassan, and along with my colleague Jinghan Yao, we'll be presenting this tutorial, which on a high level, the purpose of it is to basically provide some insights into the application side of things. So when we talk about deep learning, what sort of patterns when it comes to the computation and the communication, what sort of patterns do we see for different workloads? So for both the training and the inference. And then we're gonna review some of the state-of-the-art solutions and frameworks that are optimized and specialized for these specific workloads. Okay, so this is the outline. We're gonna start with a very high-level introduction and then move into training, talk about background about DNN training, distributed deep learning, both data parallelism and sharded data parallelism. We're going to review some training solutions. And then on the inference side, we're going to talk about tensor parallelism and expert parallelism, which are also applicable to the training. But since they are also present in inference, the same principle applies. And then we're going to finish with the conclusion. And by the way, feel free to stop me at any moment if you have any questions. So very general question, what is machine learning? What is deep learning? Most of us already know, but the formal definition is for machine learning, ML, is that it's the study of computer algorithms to improve the automation of learning from the data. And deep learning is a subset of ML that uses DNNs, hence the name deep, right? So the network has 2 or more layers. It's a deep network, and it's the most important subset of AI. So we have AI is the larger subset. Within it, we have machine learning, and then within it, we have deep learning. The main difference between machine learning and deep learning is that with ML, feature extraction happens manually, That is, if we have an input, let's say a picture, features need to be extracted first. So whether vertical lines or horizontal lines or color, these are features that are fed into the model. The model then decides how to make sense out of these features. Maybe make a classification. Is this a car? Is this not a car? And then with deep learning, the feature extraction happens automatically. It's part of the model itself. It's embedded within the model. So that's why it's a very powerful tool to use DL. But the main challenge is that we need a lot of data to train these networks. So this is an overview of the history over the past 200 years. So we start with linear regression, which is more of a mathematical principle rather than a machine learning principle, but it's still very much used today. And then after that, we have the PCA, principal component analysis, Turing machine. But when the perceptron was introduced by McCulloch and Pitts in 1957, that's when the golden age, the first golden age of AI started. And the perceptron is just a neural network with one layer. So it has weights, it takes inputs, it has weights, and then gives output. So the golden age lasted until the introduction of the XOR problem. And the special thing about the XOR problem is that it has nonlinear data, right? So your data is, if let's say it's on a 2D plane, you cannot simply draw a line and separate your data. Whereas all of the previous solutions were linear in nature. So that's why the dark age or the AI winter of AI started. And like one of the major godfathers of AI said, Marvin Minsky said that, okay, the perceptron will never be able to solve nonlinear problems until the introduction of the multi-layer perceptron. So if you have multiple layers, perceptron with multiple layers, and then between these layers, you have activation functions, nonlinear activation functions, you can train this model to map nonlinear data, which is a very powerful thing to do. But then after that, the main challenge became the computation, right? We don't have enough computational power to be able to process these large models with basically a lot of data. And that is until the introduction of AlexNet in 2012 by Alex Krzyzewski. He introduced this CNN, convolutional neural network, which is not a new thing, but since we had access to GPUs, they were able to train it on the ImageNet dataset, a very large dataset. It performed very well. We got, after that, ResNet, an improvement. And then in 2017, transformers were introduced, and a paper called Attention is All You Need, a very important paper. It gave us BERT, it gave us GPT, and all of the fancy large language models that we use today. And speaking of fancy large language models, they are mostly on the generative AI side of things. So if we think about your Llama, GPT, Gemini, all of these models are generative in nature. And that is, they take data, they learn on that data, and then they generate similar patterns, right? So it's generative in nature. And generative AI is a subset of deep learning. And it's not only applicable to text, it's also applicable to images. So we have diffusion models like DALL-E and Stable Diffusion, which the purpose of these models is to generate new images. We have also video models like Runway and Sora, and even audio models. So generative AI is not discriminative. So that means other tasks like classification, regression, and object detection, all of these tasks are not fit for generative AI. You need specific models for them. And even for clustering, you need like unsupervised models. Usually we use machine learning for these sort of tasks. So generative AI is very good for specific thing. Some people try and use them for other sort of tasks, but that's not the best of idea. That's why we see sometimes that these large language models have shortcomings. They are limited because people try and use them for these tasks, but in reality, you can train like a specific model to perform better on classification. Okay, so I mentioned that we're going to talk about training and inference. What is the main difference from a computational perspective? With inference or with training, we have both the forward and backward pass. So the forward pass is basically a scan of the model that goes from the input to the output. So we generate one output, one prediction. And the backward pass, we look at that prediction, we compare it to the correct answer, to the ground truth, and then we run the backward pass to basically adjust the model weights so that in the future, if it sees similar input, it performs better. With inference, we only have the forward pass, right? So we only want to generate the output. That's what we are interested in. So there is no need to adjust the model weights. And generally, the forward pass is 1/3 of the computation. Okay, so backward is 2/3. The forward is 1/3. So we can say that inference, one pass of inference is 1/3 of the computation of one pass of training. Now for generative AI, it's slightly different. So the previous slide was, okay, inference in general, that's the case. But with generative AI, things happen in an iterative loop, right? So we've all used ChatGPT before. You first feed a context to the model, you feed it a query, and then tokens get generated one at a time. The reason for that is that the model needs to attend to every token, whether it's in the context, in the original question, or the new output that is being generated. So every token that is generated is used in the future by the model to generate the token after it, right? So it's an iterative loop. There is a dependency. And with that comes a lot of inference-specific metrics that we need to satisfy. There are quality of service requirements that we need to keep in mind. One of them is the low latency. So we need to ensure that response time is short. That is the time to first token. And also the latency to generate token after token. It should generally be lower than the reading speed of a human. And then efficient batch processing. If there are many, many users, we also need to keep that in mind, be able to provide high throughput while maintaining the latency. We also need to have support for mixed precision. So models nowadays are stored in FP16, BF16, int8, even though training might happen in mixed precision, right? But the inference happen usually in these smaller data types. And then obviously we need high-speed interconnect. That is because we use parallelism for larger models, and we might also separate stages of the inference where communication between these stages is needed. And finally, we need high memory bandwidth, whether it's within the GPU itself, that is the HBM. So even HBM is very fast. In many cases, it becomes the bottleneck. And like memory between the CPU and the GPU and on the network itself. Okay, so this is an example of a deep neural network. It's a very simple instance of a DNN. We have 3 layers, so we don't count the input layer as a layer, right? So every layer after the input, this is what we count. We have 2 hidden layers and the output layer. And during the forward pass, we feed the input X. We propagate it forward, right? So it's just a simple multiplication operation where we multiply X by the weights, W1 and W2, and we propagate it to the next layer. And for each one of these circles, these are neurons, we have an activation function, a nonlinear activation function is either ReLU or the tangent function. And finally, we have an output, a prediction. We calculate the error or the loss by comparing that prediction to the ground truth, to that correct label. And then once we have that loss, we can propagate it back and we calculate the gradients. So the gradients will tell us, okay, in which direction should we change the weights of the model in order to make it more accurate. So if it sees similar data in the future, it gives us the correct answer. One very important concept to keep in mind when it comes to DNN training is the learning rate. So as I said, Gradient will tell us in which direction, but learning rate will tell us, okay, how much do we trust this direction? How big is the step that we want to take when we update our model weights? So if it is too low, that means we need many, many steps to basically minimize the error. So this function j of theta is the error function, and the objective is to minimize it to find a minima. And then theta is the parameter, the parameters of the model. So too low, many steps, it's going to take a long time. Too high, it might diverge. It might never converge to the minima. And then if it's just right, it's going to be the optimal, right? It's going to converge as quickly as possible. So this is a hyperparameter that the user needs to basically optimize before the training starts. Another important concept is the batch size. So this algorithm of forward pass and backward pass calculating the gradients is called gradient descent. It comes with different flavors. One of them is the batch gradient descent, where if we have a data set of n samples, the model will do a forward pass on all of these samples, calculate the error for every single sample, and then do the backward pass and do the model weight update, which is based on seeing all of the samples. But this is, first of all, this is very slow, right? You only take a step after seeing the whole data set. And also it's resource intensive. So one other option is to cast the gradient descent, where we pick a batch size of 1, we sample a single data point from the data set, and based on it, we do the forward pass, the backward pass, we update the model weights. This is also not very efficient because now we have many, many steps. So there is a sweet spot between these two options. It's called mini batch gradient descent, where we still randomly select data points from the data set, but now we put them into mini batches. Batch size can be like 64, 128, and so on. And then once we complete a full sweep over the data set, this is what is called an epoch. And to train a model, we need to run it on the data set for many epochs. So many steps, and then these form an epoch, and then we need many epochs for the model to finally converge. And then this is some of the actual like model architectures when it comes to language side of things. So things started with, I would say, the major basically model in the past is LSTM 1997. Since then, models were very limited in their context. They were only able to look at maybe 5 or 6 words in the past until the introduction of the transformers, which uses attention. And from transformers, we have these two families, BERT and GPT. BERT uses the encoder part of the model, whereas GPT uses the decoder part of the model. And then from GPT, we got the GPT-2, 3, 4, and now 5. But you can also see the trend of the model sizes increasing exponentially. So just between 2019 and now, it went, like the model size went from a few hundred million parameters to now trillion of parameters. So that means, yes, the models are getting better, but also the computational requirements are growing. We also see the same trend when it comes to computer vision. We have also 2 families for computer vision. One is the CNN architecture. So that started with ConvNet and LeNet. And then, as I said, AlexNet was introduced later on, and more deeper and bigger models were built on top of that, like GoogleNet, ResNet, and so on. But we also have the other family, which is the vision transformer architecture. So after the introduction of the transformer and it being used for language models, computer vision side, or the researchers found that, okay, these are very good models. They can be generalized on many different tasks. Let's use them for vision. And hence the VIT model was introduced. And now the state of the art is the VIT, but really the best of the best models use both VIT and CNNs. So you'll see both the convolutional operation along with attention in one model. It's a hybrid. So that's basically for the background of DNN training. Any questions so far before we continue. I know this is common knowledge for everyone, but we had to cover it anyways. Okay. So now let's go to the distributed part. As I said, the language models are growing in size. We went from RNNs to transformers to BERT, GPT, and Llama. Vision models as well, from the AlexNet, ResNet, and now we have the vision transformers. They require a lot of memory, a lot of computation, and large models cannot fit in the memory of the GPU. Also, so maybe that is true, but also for vision transformers, most of them do fit in the single memory of the GPU, but they require a lot of data and large data samples, right? So that makes them too large to fit in the single GPU. So the model weights themselves may fit, but once you introduce a lot of data samples, large data samples, that's becomes a problem. So single GPU cannot really keep up. Community, maybe 5 years ago or 6 years ago, we're relying mostly on the like single node, multiple GPUs. But later on, since we are limited in the number of GPUs that we can fit in the single node, maybe like 8 or 16 maximum, people have moved to the multi-node. So distributed training, multiple nodes on the system, each node has multiple GPUs. And we have many different flavors when it comes to parallelism. So one of them is data parallelism, which is probably the most common, the most used, where we have, if we have multiple machines, 4 machines, each machine will hold the full replica of the model. So the same exact copy on each of the machines. And then each machine will be fed different data samples. And then a synchronization operation needs to happen so that all the models learn the same thing, right? We don't want to train 4 different models. We want to train one model, but replicate it on different machines. So data parallelism is very good if your model fits in every machine. If not, you need model parallelism, where you split the model itself across multiple machines. The problem with that is there's basically dependency, right? So machine 1 will output activations that is used by machine 2 and machine 3. So whenever machine 1 is done and the second layer starts processing, machine 1 will become idle again. So at most, you'll have one or more than that, one or more GPUs that are not active, right? So you have a lot of idle time, you have wasted resources. So that's why we need hybrid parallelism, where we combine data parallelism and also model parallelism, so that we can get the best of both strategies. So this is a more detailed overview of data parallelism. It has basically 3 stages. First one is the data propagation. So we have a large data set. We're going to take a batch from that data set, and then the batch itself, we're going to split it across all of the machines. And as you see, we have GPUs 0 to 3. Each one of them has the model parameters, so a full replica of the model parameters. And then based on the data that is fed to that machine, we're going to do the forward pass to generate the predictions, right? Calculate the error, and then do the backward pass to generate the gradients. But now each machine has different local gradients. So since each machine sees different data, that's why we need MPI or reduce to basically sum all of these local gradients and then broadcast them back so that we have the global gradients. And the global gradients now are used to update the model parameters. So only when all of the machines have the same gradients do we do the model update. And this is just one iteration, one step. So this is done until we pass the entire data set, and then this is one epoch, so we need it for many epochs. So you can see that MPI reduce is used many, many times during the training, which means it needs to be very good. It should not be a bottleneck. And we also need to find a way to overlap the communication and the computation. So as I mentioned, data parallelism works very well if the model fits in the memory. And usually the communication overhead is minimal. So you'll get like 95% efficiency. But now what if the model does not fit? Can we still use data parallelism? And the answer is yes. Deep speed zero, or fully sharded data parallelism from PyTorch, is a technique that is used to shard the model weights, gradients, and optimizer states across multiple GPUs. So the baseline is just the data parallelism, right? We said we have a full replica of the model on each GPU. So that's a lot of redundancy, right? You have the same model weights, but each machine sees the full model. Can we do better than that? And by the way, the green is the optimizer states. These are states that are needed during the training, but after the training, you can discard them. They are not needed for inference. Gradients, we talked about gradients. And in blue, we have the parameters. So the first stage of deep speed zero is to shard the optimizer states. The green part is the biggest chunk, right? So we can shard that across the multiple GPUs. And whenever that shard is needed by the other machines, we're gonna communicate that shard to them. The second stage is to shard both the optimizer states and the gradients. And then the final stage, 0.3, is basically when we shard everything: parameters, gradients, and optimizer states. And as you can see, that row in the middle will show the memory requirement. It goes from 120 gigabytes down to 2 gigabytes. So instead of being limited to the device memory, now we are limited to the aggregate memory of the system. However, as you can see at the very end, the communication volume also increases, right? So for the first two stages, it remains the same. Overlapping communication and computation becomes a bit more difficult, so you'll see slightly worse performance. But then with the final stage, there is a trade-off, right? Now your communication volume will increase. And the main communication algorithm that is used here is reduce scatter and all gather. So reduce scatter is used to communicate the parameters, and the all gather is used to gather the gradients. So the question is, since zero removes the limit of data parallelism, right? Now we're not limited by the memory. Is that the answer? Is that all we need, or do we need something else? And in reality, deep speed zero has its limitations. If, let's say, one layer of the model is too large, or one matrix multiplication operation is too large to fit on the single GPU, we need something like model parallelism or tensor parallelism. And then we can combine multiple parallelism techniques like tensor parallelism, data, and pipeline parallelism. And this is actually the state of the art, Megatron LM. And Jinghan later on will talk about tensor parallelism, and we'll see how the matrix multiplication is basically divided across different devices. Okay, so before moving on, any questions on this? Okay. So now let's review some of the training solutions. This is the NVPitch MPI stack that is specific for ML and DL workloads. We call it MPI for DL. So on the very high level, we have the MPI, the ML or DL application. So that's your training script. Underneath, it might use different training frameworks, either TensorFlow, PyTorch, or MXNet. And under that, we have the distributed training middleware. So this is the software that is responsible for implementing the data parallelism, the sharded parallelism. So, for example, we have Horovat, which is compatible with the different frameworks. Under PyTorch, we have Torch Distributed, and then Deep Speed. And then under that, we have the communication backend, which can be NCCL, RCCL, or MPI. So in this case, in our stack, we have NVPitch for CPU training and NVPitch Plus for the GPU training. And of course, this stack is available on our GitHub, and also we have a user guide on the HiDL website as well. And we've recently had a release, the HiDL 2.0 stack, and it has support for PyTorch 2.7.1 and later versions. It has full support for Torch DDP, the distributed data parallelism that I talked about. And we have optimized MPI communication to make things run faster, right? We want to alleviate this communication bottleneck as much as possible. So we have efficient large message collectives like OReduce for both CPU and GPU. We have GPU direct ring and two-level multi-leader algorithms. We have support for fork safety, which is a very big thing in deep learning frameworks. Many of the MPI libraries struggle with supporting DL frameworks because of this very reason, but we have full support for fork safety and MVPitch. And then this stack also exploits the efficient large message collectives and the MVPitch Plus 4.0 library or later. Also, we have an open source fork of the PyTorch framework. It's available on the GitHub page, in which we basically optimize the MPI support because it's the PyTorch itself, PyTorch library will have the support for the CPU, but when it comes to the GPU, you'll see problems. That's why you need this specific fork to work with. And then since MVPitch is vendor neutral, by extension, this HiDL stack is vendor neutral, so it will work on different interconnects like the InfiniBand Slingshot, different GPU and CPU support, your NVIDIA GPUs, AMD GPUs, and then the software stack, we recommend using these software versions to get the best performance. And then these are some of the numbers that we've collected comparing both the Nickel and MVPitch Plus library. So this is a Torch distributed application, and we're using the GPT-2 model. We're doing training with the Nano GPT framework code base. The hardware here is on the Vista system at TAC. We have the Grace Hopper 200 super chips. Each has the 72 ARM CPUs and H100 GPU, and then the NVIDIA NDR for the interconnect. These are the software versions, and then if you look at the numbers over there, you'll see that both the Nickel and MVPitch Plus performance, the throughput, this is the time per iteration, right? So lower is better, and we go from 1 GPU to 64 GPUs, and we see that the scaling is nearly linear in both cases. But the main advantage of MVPitch Plus is that it is vendor neutral, right? So wherever you install it, it's gonna give you the best performance compared to the other libraries. And this is basically the same exact experiment, but now on AMD GPUs, the AMD MI250X on the Frontier system. And this is also the milliseconds per iteration going from 1 to 8 GPUs. This is within the single node. And then going from 16 GPUs to 128 GPUs on the multi-node. This is comparing Brickle and MVPitch Plus. And as you can see, as we go beyond the single node, we start seeing slightly better performance when we use MVPitch Plus. So up to like 12.4% less time per iteration. So both of the two applications that we saw earlier were on the GPT model, right? So language modeling. This is an experiment with the ResNet model, so a vision model on up to 1,500 GPUs. And the training is happening on 1.2 million images. So that's the entirety of the ImageNet data set. Time per epoch, if we scale on 1,500, becomes 3 seconds. So if we train this network for 90 epochs, the whole time that is needed is 4.5 minutes. And this is on the Summit system. And then this is the same experiment, ResNet model on the ImageNet dataset, but this is on the CPU. So this is on Frontera, and we scale on up to 2,000 CPU nodes. And we see that if you have enough CPU nodes, right, which are relatively much cheaper compared to the GPU nodes, you can still get very good performance. So with the 2000 nodes, now training can be done in 7 minutes, right, compared to 4.5 on the 15,000 GPUs. 1,500 GPUs. One more thing. So when we're talking about data parallelism, we said that the model fits in the memory of the GPU, but what if the model is very small, right? Now we have these very powerful GPUs like A100 and H100 and the Blackwell. So some of the models which are still very much used today, like the ResNet 18, the ShuffleNet, VIT tiny models, these are very important for edge devices if you're performing inference on the edge, but you still need to train them. And you want to train them on powerful devices so that it happens quickly. So what we saw is that like a GPU like A100 using this device for training ResNet will be wasting a lot of resources. So most of your GPU will be underutilized. That's why we introduced this idea of fitting multiple replicas on each GPU and using MPS from NVIDIA to basically treat each replica as its own MPI rank. And we see up to 30% and 62% improvement across different workloads. Finally, we have this MPI for DL package. It's based on PyTorch, and it's directed at workloads where the images are too large for any GPU to be able to process them. So even though the model might be small, the image is too large. So the image is the limitation. That's why you need more advanced parallelism techniques like layer parallelism, pipeline parallelism, or spatial parallelism, where the convolution operation or the attention operation itself is split across devices. And these are some of the numbers with this package. You can also find it on the HiDL website. So this is just comparing different parallelism schemes and the sort of throughput that you can expect out of them. Okay, so with that, this is the training part. Do you have any questions before we move to the inference part? Yes.
I'll just say that.
Sure.
So on the GH200, your numbers were basically you forced it to be only network-to-network communication, right? You kept the CUDA out.
What do you mean? Could you elaborate?
The GH200?
Yes.
Yeah. So, so you are saying one GPU per node.
Yes.
There's no NVLink.
That's the setup. Yeah, that's the setup of the system.
There's no NVLink connection.
No.
And so at that point, you're basically this code path is comparing what Nichols optimized path selection would have been versus your path.
Yes, exactly. Yeah. Any other questions? Okay, so with that, let me hand it over to Jinghan to talk about the inference part. I mean, you can take
So hi everyone. I'm going to briefly introduce the some techniques in inference. Let's start with a quick background. So we see a lot of parallelism used in both training and inference, but in inference we have we care about different things. We prioritize different things. So up there you will see there is a table that is from the Meta Llama 3 technical report. In the table you will see there is something called MFU or T-flops. So basically in training, you only care about the throughput of your clusters, right? But in inference, we first order for the latency and then we maximize the throughput because let's take the LLM serving as an example. We have some service level objectives in the, when you serve the LLMs in companies like, OpenAI or Anthropic. So we call them SLOs. So there are two very important SLOs. The first one is TTFT, which is time to first token. This has to be less than seconds for the. Otherwise, the user is gonna wait for a very long time to get the answer. And the second metric here is time between tokens, or TBT. This has to be less than 25 milliseconds, which gonna meet our human read speed, basically. So our goal in inference is like, how do we really reduce the latency? Whatever it's computation or it's communication, we just want to, meet our SLOs. Sure. And let's see how do we actually optimize these latencies. So the first technique I'm introduced here is tensor parallelism. It's not a new thing. It's widely used in training from many, many years ago. I'll first explain how it works briefly. So originally, let's say you have your batch of input and you have your model weights. So basically you perform this matrix multiplication to get your final results. But in tensor parallelism, what you do is, so each GPU, let's say you have 2 GPUs right now. So you split your input data and the model weights, one horizontally, one vertically, and then you perform 2 matrix multiplication on each of the GPUs. On each of the GPU, you will get a partial sum of this matrix multiplication. And at the end, you perform the OR reduce to combine the results together. So some of you might notice that even though I split the matrix, like each GPU only do half of the work, the final results will still be the full matrix, which is the same size as you do not use tensor parallel. So one thing you will notice here is that as you increase the number of GPUs in tensor parallel, you're actually adding a lot of communication volume, because you will get a lot of partial outputs needs to be OR reduced. So yeah, so in inference, yes, we still use TP, but as I said, TP will increase the communication volume. So in inference, we use TP is mainly to reduce the latency of loading the model weights, not for computation perspective, because here you can see that in the TP case, each GPU only needs to load half of the matrix, the weight matrix. So this is why we use TP in inference. It's not we're trying to, reduce the computation or accelerate the communication, no. Cool. So then I will quickly go to expert parallel. So this is something relatively new. It's proposed several years ago, but we see a lot of new techniques regarding expert parallel in these days. So quickly, so expert parallel is used in mixture of experts, which basically think of you have originally you have a very dense matrix, like right on the upper right corner. Like originally you have a dense matrix, but now you are trying to split this giant matrix into multiple small matrices, and we call each of them as expert. So one thing in inference, like that is different from training, is that in inference, we say the MOE is very, very sparse. So for example, if your language model is only decoding 1 token at a time, that means among all your experts, only 1 expert will be activated in this inference. So it's basically like most of them are not used during inference. So it's very, very sparse. So there are 2 ways to distribute your mixture of expert models. The first way is that you can still do it in tensor parallel manner. Basically, if you have 4 experts and you have 4 GPUs, the tensor parallel strategy is basically you slice every one of the experts and place it in one of your GPUs. So in this case, expert 0 goes to all of the GPUs with computation happens on all of the GPUs, and the same for other experts. So here you can see that for 1 token, the overall communication volume is 4 by the size of the token, because each GPU will only get a partial sum and need to perform the OR reduce. And why tensor parallel is not widely used in MOE is because if you look at expert parallel, where we put each expert solely on 1 GPU. So in this case, let's say you're still decoding 1 token. This token only needs to go to 1 GPU. After computation, it goes back. So here, the overall communication volume is this. So you go to that GPU and you come back. So 2 times the size of the input token. And the fact is that the more GPUs you add to your clusters, the gap between TP and EP becomes bigger, because in TP, you always have to you will get a lot of partial sum. Basically, that's the rule of matrix multiplication. So that is why expert parallel these days all use this kind of expert parallel strategies. Cool. And as we said, there are 2 OTO operations in each one of the layer of your model. So if your model has, let's say, 3 layers, you will have 6 OTO operations in total, and all of them are blocking operations, which means that there are strict data dependencies there. So as we said, we care about latency in inference. And with all of the OTO communications blocking the computation, how can we reduce the latency? So this is actually a very hot topic these days, and this is something we are planning to do with our software stack. So the general idea is overlapping your communication with computation. So what you see here is a very naive version of overlapping. So let's see, we are processing 2 tokens, or we see we have like 2 batches. So this is very simple. You create 2 streams. On stream 0, you only process the first token, right? You have attention, and then you go to the first OTO operation. And meanwhile, you can because this communication, it does not occupy your tensor cores basically. So at the same time, you can use your computation cores or like tensor cores to do the attention operation on your second token. So this is basically very, very coarse-grained overlapping strategies. The issue with this kind of a design is that nowadays we see GPU communication libraries like Nico or Rico, they gonna reserve a lot of SMs to perform this, RDMA read and write. So a very simple example here is that if you look at the Nico defaultly reserves up to 32 or 64 thread blocks for communication. And the thing here is that if your communication libraries reserve so many thread blocks, that means your computation gonna be performed with less SMs. So this will reduce the throughput of the matrix multiplication that you're trying to perform. And also this communications only use CUDA cores, which means that you're wasting all of the other powerful tensor cores on your GPU. So this is the problem with existing libraries. So there is a very, very new technique. It's called, the techniques is not new, but the application by using these techniques in the MOE is very new. So it's called InfiniBand GPU Direct Async, or IBGDA. So the thing here is that can we perform some fine-grained overlapping, that is better than the previously mentioned, multi-stream method. So in this IBGDA settings, basically you will see a lot of put instructions inside your kernel. Actually, get is less common, but almost all of them are just put. So basically inside your GPU kernels, right after computation, some